Hello friends, grab your coffee, grab your cookie, and try not to drop either near a cutting wheel, because today we are talking about ferrous metal dust, also known as steel dust. It may look harmless like gray powder on your shop floor, but in reality it is abrasive, conductive, reactive, and regulated under NFPA 484 if the particle size is fine enough. My name is Michael Klepik. I design dust collection and air filtration systems for steel fabrication, machining, foundries, and recycling plants. Let me tell you exactly why steel dust deserves respect. What ferrous metal dust really is, technical definition. Steel dust forms during grinding, cutting, milling, drilling, polishing, blasting, or welding prep of carbon steel or stainless steel alloys. Technically, first, particle size can range from 1 micron to 300 microns. Second, the most respirable and airborne fraction is from 1 micron to 20 microns. Third, bulk density is extremely high, generally from 4,500 to 7,500 kilograms per cubic meter. Fourth, dust composition may include iron, carbon, chromium, nickel, manganese, molybdenum, and alloy-specific oxides. Fifth, fine steel dust oxidizes quickly, and recent studies show oxidation can increase particle temperature inside dust layers. Put simply, steel dust is heavy, reactive, and airborne in its finest form. Where steel dust appears in industry, steel dust is generated in: first, precision grinding and finishing operations; second, CNC machining and automated turning centers; third, abrasive cutoff wheels and flap disc grinding; fourth, foundry shakeout and gate removal; fifth, structural steel fabrication and rebar cutting; sixth, blasting, peening, and heavy surface prep; seventh, metal shredding and recycling lines. Wherever steel is shaped, dust appears, guaranteed. Why steel dust is dangerous? The real hazards. Steel dust creates several severe risks. First, fine ferrous dust is combustible under NFPA 484 criteria. Second, steel dust oxidizes rapidly, producing heat and reactivity. Third, it is extremely abrasive and erodes fans, ducts, and filters. Fourth, steel dust is conductive, causing short circuits in electronics. Fifth, stainless steel dust contains chromium and nickel oxides, which pose additional health hazards. Sixth, dust layers increase the risk of secondary deflagration. Steel is safe when solid, but a different material entirely when reduced to dust. Combustibility, oxidation, and static charge. Here is what makes steel dust reactive. First, when divided below 50 microns, iron particles can ignite if exposed to sparks, hot surfaces, friction, or oxygen-rich environments. Second, carbon content and alloying metals change combustion behavior. Third, stainless steel dust oxidizes slower but still contributes to dust events. Fourth, steel dust is conductive and accumulates static charge inside filters. Fifth, oil-contaminated steel dust ignites much faster than dry dust. Ignition probability increases with surface area and temperature, meaning smaller particles are far more dangerous. Behavior of steel dust in airflow systems. From an engineering perspective, first, heavy steel particles drop out of low-velocity ducts. Second, fine dust behaves like heavy smoke and stays airborne. Third, magnetic particles cling to steel ducts and fan housings. Fourth, abrasive dust wears down elbows, dampers, and inlet cones. Fifth, steel dust packs tightly inside filter media, increasing pressure drop. For ferrous dust, I designed duct velocities from 4,500 to 6,000 feet per minute to prevent settling. Filtration equipment that works. Best, faux EHN cartridge collectors. Great for fine dust. First, high-efficiency media captures sub-micron particles. Second, conductive and anti-static filter media prevent spark hazards. Third, strong pulse cleaning removes tightly packed iron oxides. Baghouse Blizzard ideal for heavy steel grinding dust. First, it tolerates large volumes of coarse metallic particles. Second, abrasion-resistant bags last longer under heavy loads. Third, inlet baffles protect filters from direct impact. Abrasion control essentials steel dust requires: first, abrasion-resistant elbows. Second, ceramic or AR steel liners. Third, properly positioned baffles and dropout sections. Without abrasion control, even new ductwork wears out fast. OSHA and NFPA compliance requirements, steel dust falls under OSHA first. General duty clause enforcement for combustible dust. Second, metalworking standards for hot surfaces and spark sources. Third, permissible exposure limits for iron oxide fumes. Fourth, mandatory dust hazard analysis for dust-producing operations. NFPA 484, combustible metals. standard for steel dust, NFPA requires: first, explosion venting on dust collectors when applicable; second, duct isolation valves to prevent flame propagation; third, anti-static media and conductive ducting; fourth, grounding and bonding of all metal components; fifth, no plastic ducting for conductive dust; sixth, proper spark and fire prevention systems. Compliance is essential for safety and insurance coverage. Capture hood design for steel dust workstations. To reduce airborne steel dust, I designed: first, fully enclosed grinding hoods; second, downdraft tables for welding prep; third, multi-stage capture for robotic grinding cells; fourth, high static extraction arms for manual grinding; fifth, capture at CNC enclosures and chip ejection areas. Good hood design prevents steel dust from settling inside ducts and collectors. Ferrous metal dust, also known as steel dust, is dense, conductive, abrasive, partially combustible, and highly reactive when finely divided. It damages your equipment, your ducts, your fans, and, if NFPA 484 is ignored, can contribute to ignition or explosion events. With proper airflow, abrasion-resistant design, high-efficiency filtration, and full OSHA and NFPA compliance, we can manage steel dust safely and efficiently. I am Michael Klepik. Protect your lungs, protect your equipment, and remember, steel belongs in your parts, not floating through the air. See you in the next video.